recording, and I'll now initiate my coverage of this concept of Grothendieck topologies and sheaves over them, which really brings together a lot of ideas we've been exploring in the class. And then, as time allows, go on to talk about sheaves and sites. So, a few high-level points. General notions of topology that we've talked about allows reasoning about connectivity and continuous deformation in a way that preserves locality. But as the book notes, there's quite a few needs for sheaves that do not fit into this context. And I was interested to see that Grothendieck in Sheaf Theory Through Examples gives reference, for example, to a notion of topology that might apply for strings in a more generalized sense, without this notion of continuous deformation. And as we'll see, this notion of sites with Grothendieck topologies provides a simple means of using a general category to define a sheaf. That's really mangled there. Grothendieck topologies that we'll be covering provide an avenue for defining Grothendieck topoi, or topuses, which are extremely useful constructs outside the scope of this course. They use machinery from general categories, families of morphisms within categories, and they admit several versions with growing generality. As I had noted in my opening remarks earlier, the first and more simple of them, which does have the disadvantage, such as it were, of depending on the existence of pullbacks, will suffice for our needs. But we will get us to the cusp of being able to define these topologies more generally through sheaves in this context in this session. And as Grothendieck notes, many intuitions from topology carry over to this area, even though we have a more general notion of what it means to be a site for a sheaf. Now, I need to give credit where credit is due, and the presentation here, as always, for this course is drawing heavily from sheaf theory through examples. But I also want to refer you to, if anyone's interested in going a bit deeper, or really, getting a nice presentation, I'd refer you to Daniel Chen's Grothendieck Topologies video online. Daniel Chen is a professor of pure mathematics at University of New South Wales in Australia. And he gives a very nice treatment of some of the materials which are present in this chapter of the book. So to do justice to this chapter, and to do justice to the notion of a Grothendieck topology, we do well to remind ourselves of some background material. And I think you'll find that if you reflect on this material, the definition of a Grothendieck topology will at once be more accessible and more intuitive. So I'd like to sort of lead up to the definition of a Grothendieck topology by reviewing some material, and then we'll actually go through that definition in a way that will further tie into some of our earlier material. So you'll recall that from this chair, many weeks back now, we defined the notion of a topology. And we talked about a very set theoretic definition of a topology. If we have a set X, we have a collection of subsets of X. You could think of these as elements of the power set of X, right? And we called this collection of subsets tau. And tau had some axioms associated with it, some stipulations, some rules. It has to contain the empty set. It has to contain the full set X, right? Excuse me. And it has to contain the arbitrary union of elements over tau. So this is kind of recursive components of this. When we say arbitrary union, it could be in principle infinitely broad. So when we were dealing with the usual topology and say R squared in the plane with real numbers in both directions, both coordinates, or in R cubed. There we might need an infinite number of unions of small balls to fill in certain spaces. You'll recall that we could take unions of elements of tau, and those unions have to be in tau, and finite intersections. And it's suffice to say we have to support pairwise intersection because from that we can get finite intersections. And you recall that these elements of tau were called the open set of the topology.
Can you share slides actually?
Oh, I'm not sharing slides. Thank you. Thank you. No. Okay, thank you. That's awesome. That's awesome that you caught that. Okay. So that's great. Yeah. And I'll note that, we commented at the time that this definition, while it was very set-based, and it started with a set and it built up a collection of subsets of that bigger set X, it imposed structure beyond what's in X as a set itself by defining the relationships between those things. In fact, we could take unions, and those would be in the topology. We could take finite intersections, and those would be in the topology. That led to extra structure beyond what we saw in X. And that extra structure, we argued at the time, captured a notion of neighborhood, locality, and it was sufficient to reason about things like continuous deformation that preserves nearness even while it may stretch a space, for example. So you recall topologies. And what we're building here is a generalization of it that also captures structure, but through categories and the properties associated with that structure and categories. You recall, though, with a traditional topology, if we had some set U, when we had a cover, of a set U, we could arrange a description of this in terms of subsets that collectively covered the entire set. And if I had better presence of mind, I would have shown each of these arrows here as an inclusion, showing that, for example, U1 and U2, the union of them are included in U. In other words, they're a subset of U. U1 union U3 are a subset of U. U2 union U3 are a subset of U. And collectively, what this is showing is that U1, U2, and U3 are all subsets of U, and the implication here was that they covered U. But I want to remind us that we are dealing here with a category of sets. That's what these are. And inclusions. The arrows indicated inclusions, indicated a subset relationship. Are we good with this? We good with this idea? Okay. Okay, I also wanted to, in the African savanna, they say that watering holes, if you want to see the animals in the savanna laid out in front of you more easily than going around and tracking them down, you stay by a water hole. And you stay by a water hole for a couple of days. And you will see the various animals of the savanna, be they in the water hole itself, or from close by or far-flung areas, they'll make their way to the watering hole. And so it is, I think, with Grothendieck topologies. We'll see a lot of our friends coming to this watering hole, a lot of our friendly concepts. Another friendly concept is that of pullback here. And you recall the notion of a pullback, right? This generalization of product. And you recall that if we had some object C in a category and objects A and B, we have mappings from A to C and B to C, then we could construct a pullback of A and B over C, which gives us some notion of the product of A and B of things that are compatible in the sense that they map to the same C. Remember that? And for example, we had a notion from Eugenia Cheng of, if this was in set and the morphisms were functions, these were sets and the morphisms were therefore functions. And we had A as the set of pants and B as the set of shirts and C as colors, T as colors for a pair of pants, S as color for a shirt. We could take the the pullback of A and B over C, and what would we get? Does anyone remember? Yeah, pairs of pants and shirts of the same color, right? So it's a familiar notion. But I also want to draw attention to the fact that within set and the category of sets and inclusions, that we can end up with a situation with this beautiful pullback square. It's so beautiful that it's in the scarf my wife beautifully knitted for category theory. So so here we have on the lower right a union B, upper left a intersection of B, and we have sets A and B here. And all of these morphisms are monomorphisms, right? They all indicate inclusion. And I want to draw your attention to the fact that A intersect B is it's a certain type of categorical construction, that together with the square, comedic square. What is this? This is what do you think from it having this nice little thing here? This is the pullback of A and B over A union B. And I want to emphasize this. Well, noted that A union B is the push out, which is really cool. A intersect B here is what I want to focus on. And I want to make sure that you appreciate in your mind that what this is showing is the areas of A and B that overlap, that agree with what they map on to A union B, right? A union B combines both of them, and A intersect B are the parts of A union B that are in B and that are in A, right? That are at once mapped to by both of them. So here we have A and B having some area of common overlap in A union B, as indicated by the fact that this square commutes. And that's what's captured in A intersection B, okay? So I'm trying to communicate to you that the pullback of A and B over the union can be recognized as an intersection in set. That if we do that in set, we have the union down here, we have A and B, the union of A and B down here. This can be the intersection. This is the intersection. Okay. This is the intersection of A and B by virtue of the fact that there is some common ground. There are some common points to which they map, right? Just like some shirts and some pants have some common colors, and that's what's in this if C is colors. Here, A and B have some common points here, and that's what's in here. The shared points of it. Just like this is is pairs of shirts and pants of the same color. This is sort of pairs of A and elements from A and elements from B that map to the same point, namely that are in the intersection. Are we okay with this? Okay, so keep this idea in mind of pullbacks on sets as being equipped to give you unions as well. Sorry, intersections when union is down here on the wall. Okay, so this brings us to our, and I've got to manage these widgets. Okay. I want to talk about what Grothendieck calls Grothendieck pre-topology. This is actually characterized by Daniel Chen as a Grothendieck topology, and it does, I think, reflect the fact that in the book there are several definitions of Grothendieck topology given, but it basically consists of the following: a category, and I'm going to be showing notation, drawing on what I consider the best points of notation of Grothendieck and of Daniel Chen in this, because I like how each of them handles different aspects. Okay, so what is a topology here? Well, it consists of a pair of two things: a category, which is called cat T, or here we'll call it the category C. And importantly, this will have to be, for this definition, a category with pullbacks. Okay? And then a collection of covers called cov T. So we're calling the Grothendieck topology T. And there's a thing called cov T. And Grothendieck uses the term K of U for it, okay? Meaning it's going to be indexed over U, which is going to be different objects here that will be covered by different families. So K of U. It's a collection of families indexed by U. And each of those families has an object U, and that's distinguished for that family. That's what U is. It's an object in C. So U is an object in C. And the family for U is going to have a collection of morphisms from other objects, or from objects UI to U. Okay. And there might be one, there might be many. Okay. So U is an object in C. UIs are objects in C. And for K of U, for the covers of U, of object U, we'll have this family UI intersect U. Okay, actually, it's a collection of families. We'll have a set of families. Each family will look like this. It'll be a set of U maps, morphisms from objects UI into U. Okay, so each U is going to have a collection of families. Okay, so a given U might have many different covers. each of which is associated with a different collection of morphisms from objects to object U. Notice I don't say there, this doesn't say this has to be a monomorphism, just it's a morphism, okay, in our category. Okay. Now, if we have this, if we have our category, we have our collection of families, we're going to specify some further axioms. First of all, the topology, the K of U, for any isomorphism involving U, like this one here, U prime to U, including with itself, then K of U includes that isomorphism. So K of U is a singleton family. K of U includes many families. It could include many families. But one of them is for every isomorphism with respect to U, and there's a singleton family just consisting of that morphism, just U prime to U. Mind you, if you think about it, every object, for every object C in a category, ID of C constitutes an isomorphism, goes to itself. And so it always includes a morphism. K of U always includes a morphism U to U. That's identity, right? It's a singleton. And really what this is saying is the topology includes the entire set. After all, X is itself. Conceptually here, there's some object that for any covering of U, there's going to be a U goes to U. And so it's going to include the relevant topology there is going to include U itself. It also includes conceptually empty set, because any initial object here, for example, the empty set, will have a morphism to itself, and therefore will be also included in the topologies. Okay, so you could think of this as kind of analogous to when we had a topology, we said it has to include the empty set in X. Okay. And it may be that we could derive, here we could derive these. This was like the union of no elements. This was the empty intersection. And it may be that we could do something similar here. I haven't thought it through. Okay. So that's one fact. The second is this covers via composition. So the idea here is, it involves notation, but it's a fairly simple idea. Look, if you have a family in K of U that involves a set of UI with morphisms to U. So you're considering KU. KU is a collection of families, all with U as the codomain. And we consider one of those families, and it has a bunch of UIs with morphisms to U. Okay, fine. And then if we have another family in K of UI that has a bunch of morphisms from other objects to UI, then we can compose them and get a family from those VIJs to UI. So really what this is saying is, like, if we have a set of these morphisms, that's our family here, right? So our family here, which is in K of U. And what this is saying is, well, wait a minute, if each of those UIs has V's associated with it, then these V's, by composition, also form a family for U. So you could just compose them like this. It's a very sensible notion. You'll get a family for U. Because remember, in a category, any two end-to-end morphisms can be composed. So this morphism and this morphism can be composed into this, right? And so it is for all the V's. So if you think about it, this has some common sense. If these are morphisms, how could it not be that way? Well, it makes sense that if you're considering the coverings for U, that these should be on the coverings for U. Are we good with that? Okay. Now let's consider intersections. Okay. So that's the last of these. And you may wonder, like, why we talk about intersections? Well, you'll probably remember back here, we were dealing with intersections. We've just been going through these things here, and intersections are part of this picture. Okay, so here we have intersections. So let's consider if there's a family, UI to U, which is resident K of U. So if we have in our collection K of U a family like this, and now if there's another object, this is important, another object in the category V, which has a morphism to U as well. So we have some family in K of U that's going to U, right? Of these morphisms. And then we have another object in the category that goes to U in our category. C. Should be script C. Then we can do something really slick categorically. I mean, this is a very common thing categorically, but it's very slick, which is we can take the pullback, taking into account the fact that these all go to U, this goes to U. We can take the pullback of the UI and V, because we're assuming this is a category with pullbacks. And more than that, it has a morphism to V. So let's check this out. The idea here is this is our common U, right? This is our U here. See this U? Right? I see you, you see me. Okay, you didn't get that. Okay, so here's our U, right? Here's our common U. We have a UI into U, right? And we have a V into U, right? We could take the pullback of them to get this, right? Right, that's all we need for a pullback. If the category has pullbacks, we have these into morphisms into a common thing, right? Taking the pullback will give this. And the pullback gives us automatically these projections, just like taking the product will give us projections down in a uniquely defined way. So here, taking the pullback will give us these products such that this commute. Okay, so by virtue of taking the pullback, we get a morphism of this sort inside of V. Now, I say that it's slick because you'll notice both of these went to U. But now this, we have a morphism into V. So let's think what's going on. I think for this purpose, I'm going to break out the tablet here. This is a covering family actually of V. So that's why it's in K of V. Now, it is also it's also going to be a cover of U by virtue of this. Did we say that V? This is any morphism in V. I don't think we said that this is in, like, here we had this in K of U and this in K of U I. I don't think here we said that that this is a member of K of U. So I'm not sure it has to be. It's a good question. Is that necessarily cover of U? I think it will be, but I think it will automatically be yes. Yes, it will automatically be because they go to the UIs. Yes. This okay, so this also goes to UI and therefore goes to you, right? So Uja, I think you're exactly right. This will be a cover of you, will constitute a family. It'll be a family that covers you. Sorry, this going to you will also be a family covering you. Why? Because it goes through the UIs and the UIs go to you. And by virtue of this one, those will compose and it will be a family of covers for UI. But let's take a look at this if we could for this final case. So we see sort of algebraically, as it were, here in diagrammatic form how this is true. Let's consider how this is true geometrically, like just to give us something to think about. So I'm going to go to my why this is sure yet at such distance. I'm not sure. Okay. So I'm going to draw. We're going to draw. So this is one. We're going to have U. This is one UI. This will be another UI, and this will be yet another UI. And maybe U itself is in here. It's covered by these UI. Okay. So maybe to just accentuate that more, what I'm going to do is make the U look a little bit different. I'm going to make it look sort of with bigger. So this is our U covered by the UIs. Okay. Here we go. I'm going to so this will be, maybe I'll make this a little bit smaller. So this is going to be U1. This is going to be U2, and this will be U3. And this guy here is going to be U itself. Now, if the UIs were monomorphisms, they would all had monomorphisms to you. They would all lie within you, right? If the UIs, if we had UI monomorphism to you, then maybe I'll do it this way. I'll actually create one that actually has that at the cost of being kind of using a lot of colors. So I'm gonna put okay. We're done. So I'm going to call this U4. And I'll note here that U1, I'll say it first for U4. U4 has a monomorphism into U because it lies within U. Mm-hmm. There's an injective mapping from all of its points there, right? But that's not actually true for U1. Like U1 has a morphism to U. There's some mapping of it into U, but it's not a monomorphism. It doesn't lie within U. Hmm? Same thing for U2 and U3 and U3. Yeah. So, okay. So I'll just put those down here. U, and then I'll put U3 as in green. So I'll put here U3. Here we go. Okay. Okay. So here we have some geometric situation. And now I'm going to put a V. I'm going to put a V. And I just want to make sure that's right. That's right. I'm going to put maybe to, yeah, okay. I'm going to put a V here. No, I'm going to put it in a broader color. This is our V. Yeah. Get that. Okay, this is our V. Okay. So what does the intersection look like? Well, here, what do we have here? What are these intersections? Well, this area here, maybe I'll put it in this sort of color. It's too broad. Okay, fine. This is maybe, yeah, maybe I can zoom in. So, okay, so this color here, still in that mode. Okay. This little area here is going to be that little area is going to be the intersection of, what did I say this was? Was that U2 that was blue? Is that blue was U2? So this is U2. Right. Let's here. Those are mapped to the same points of U, those areas. Meanwhile, the green and sorry, okay, now I'm in trouble. No, because that it should also be this, right? And then there's going to be, so it includes all the intersection of V. V is the bright green. with U2. That's what U2 cross intersect V is there. And it is fibered over, it is pulled back over U because we are considering them within U here. I probably should have made V go outside of U just to show the points, what that would have looked like. But we are finding all these intersections that lie within U, that are mapped within U. And then similarly, this area here is going to be the intersection of U1 with I'll put in some blue here as well, just so you can see. This is the intersection of U1 with V. So U1 so we are getting the intersections of this smaller area of each of these open sets. Those all lie within V. These projections are inclusions. Yeah, that's right. This is going to be an inclusion. Is that right? I think that's okay. I'm gonna have to think about that, because if that were an inclusion, I would have expected this to be an inclusion. But no, it's certainly the case if this is an inclusion, that's an inclusion. I don't know. Don't think it's yeah. Yeah, that may be, yeah. Right. Yeah, so the idea here of this pulling back over V so that we have these morphisms, it's like we're getting the subset of all of these different coverings that lie within V. That's what this pullback is. It's lying within V here. And so they give us so like the green would cover all of this area. The dark green would cover all of this area because it all lies within the dark green, for example. So here we are considering this covering of U. Then we are considering another thing that lies within U. And actually, it doesn't necessarily lie within U, but has some components could have some components within U. And then we are taking the pullback to find the things in common between these various components and V. And that forms a covering of V. And then, as you just said, these things, by virtue of being in this pullback square, they also form a covering, or they also lie within U sub I, which forms the covering of U, and therefore they are going to, I believe, pull back in this sort of way, to be in covering of cave of U. Yeah. So what we have here is a definition of a topology that mirrors the having X itself, the empty set in intersections included. It also has this feature that if we have inclusion here and inclusion here, we can, so if U1, U2, U1, U3, U2, U3 are all coverings of U, and if U2 lies within this, then we can get coverings from this next level down as well by composition here upwards. So this composition feature occurs. You'll notice here, so this is a collection of families of morphisms like this. I don't see explicitly a union property specified here. And not clear if this collection of families must include all arrows here. If it did, then it would make sense that all unions would be included because it's a collection of all of these, and therefore it follows that if any two families are in there, their union must be in there as well. UJ, it would also follow that this must be in a family as well, and therefore its composition could actually work through this way too, to lie within U. Okay. So this is a definition of a Grothendieck topology, and you'll notice that it's operating like there's nothing here other than requiring a category with pullbacks, which is restricting it to only operate for, a special class of categories. This is a very general definition. Basically, it requires morphisms going into objects. You can define coverages there, and you can specify a structure on this that includes something conceptually like intersections, and that has features of a topology. And as a result, you can define sheaves not over just topological spaces in their classic sense, but over these topologies. To see how we do that, we're going to reflect on a little bit more here on the structure that we've built up. So the first thing is, some of these structures we've been using. The first thing is this square, and this is a pullback square. This is a pullback square involving objects UI and UJ, which have morphisms into U. And here we have a pullback over U involving UI, UJ. Oh, yeah. Yeah. We need a UE. Okay. So I think you're comfortable with the idea that if you have a pre-sheaf, any pre-sheaf, if you apply it here, given that it's a pre-sheaf is defined as C op to set mapping, these arrows will reverse, right? You're familiar with that? Right? It's contravariant. They'll go back the other way. Hmm? Okay. So keep that idea in mind because we're going to use it. I think you also remember somewhat in a like-minded way, if we had a inclusion from UI into UJ, you can get into U, you can get a restriction map this way. Remember that? So when we talk about mapping with a sheaf, these will often turn into restriction maps. Now, I also want to just reflect on the fact that if we have multiple of these, we can get multiple of these maps here. These maps down, these restrictions. And if we have this, I don't know if you remember, but this is another one of our animals coming to the watering hole. If you have an object which has a morphism like this to lots and lots of things, there's a universal construction that you can use. If you have an object that looks like this, what does that remind you of? What sort of object does this remind you of? That has a apex and then it has maps down. What sort of universal construction has that feature? Product. Yeah. So let's talk about, oops, sorry. Somehow I went to the end. Okay. Let's talk about that. So this has some of the structure of a product. But here's the thing. There's guaranteed to be a product that factorizes it, right? So you remember the definition of a product. A product is such that a product of two objects, A and B here, is a special object such that for any other object, C, which has morphisms down to A and B, the product factorizes it, right? You have a morphism, a unique morphism from C to A cross B, such that this commutes. Remember that? So the product was like the best. It was like the most parsimonious, the one-stop shop for maps into A and B. If we had any other, we could factorize it through the product. So what I'm saying is if we have a situation like this by virtue of our functor, that if we have these morphisms here in a category, we map them over with a pre-sheaf and we get something like this, we can always express this as going through a product. Right? Just any C we can express going through a product. I'm saying this is such a C. I'm not saying this is the product. I'm saying this goes through the product. So we could express it as going through the product. By going through, I mean express it in terms of the product. Are we okay with that? So I'm analogizing this to our C. It's a C in a category. And we can take a product of these things and have a morphism from this to the product. And that's what we're going to do. We're going to take this and we're going to factorize it by this product. And this is unique morphism. Unique morphism. So the product is what keeps track of all these morphisms. And this morphism is such that if you compose it, it's the same as the original morphism then. So all I'm doing is using the product, the universal property of the product. There we go. Are we okay with that? Okay. So we're going to have this sort of fragment. And that is all just leading up to this. Okay, so let's walk through it. This is a sheaf on a Grothendieck topology. So we've defined this Grothendieck topology here. and we're going to define a sheaf on it. So a sheaf here on a Grothendieck topology, cat T and cov T, is a functor. It's a pre-sheaf, such that for all families like this, for objects UI and U, and that f of u abides by this. So f of u, basically, we have this equalizer diagram applied. What is this equalizer diagram? Well, let's unpack it. The first thing is what I've shown you is sort of this working through this. Okay. So F has this unique map to this. Rather than having maps to all of these ones separately, it's going to be going through this. Okay. But it's actually simpler than that in some ways. I mean, or there's good ways to understand each of these features. Let's talk about this more. This one here. Where did this come from? Well, it came from a very specific place. We had these morphisms in our category. That's what we're positing right there. You see them? If we have our category as morphisms UI to U, then if we hit it with a functor, we get morphism from U, from F of U to all the F of UIs, right? If we have a family of morphisms like this, it's just like this, all going to U, except they don't have to be monomal. And what I'm saying, if we hit it by our functor here, now we have one that goes from F of U to all the UIs, but we can factorize it through this. We can factorize it through this. So, in short, we have F of U going to the product of the UIs. That just comes from this being hit with the functor. If the functor means this arrow flips around, and you have F of U to F of the UIs. And I'm saying if you have F to F of the UIs, that's the same as F to product of F of the UIs here. Or we can put that in there subject to the community. Okay, so this is where this morphism comes from. It comes from mapping this with F. Okay. Next, where does this come from? Well, it's a similar idea in the sense that we're going to have the pullback square. So you may remember the pullback square. We had it a minute ago. We had it. Here it is. Remember? This is the UJ pullback square. Remember that? Right? This is our pullback square. Here we go. So let's put it in here where it belongs. Here's our pullback square with UJ. Okay. There we go. We hit it with our pre-sheaf. This is what we get. We get mappings from UJ to this and UI to this, right? That's where each of these mappings come from. Pi sub j and the pi sub I are from this pullback square. Where's this pullback square? It's this pullback square here. This is our pullback. This is this. And by virtue of having that, you're going to have a map from this pullback to UJ and to UI. And then we hit it with F. And now we're going to have a map from f of ui to f of this pullback. And f of uj to f of this pullback, right? Okay, so that's where these come from. Conceptually, I like to think of this, and this is how Daniel Chen presents it, as the intersection of ui and uj. This is that intersection we tried to draw. Well, I mean, it's the intersection of the ui's and uj's. So what this is serving as is sort of what data there is over the intersection of the ui's and uj's. Okay, let's talk a little bit about this. This is this intersection. So remember this idea of pullback as intersection? That's what this is. Pullback as intersection of these two. We are pulling it back over the entirety of the U, just like here we are pulling it back over the entirety of this, right? And we get this. The UIs have these maps to U. You could take their pullback, and it's kind of like taking their intersection over the UI into which they go into. It's like taking their pullback over the entire space, the areas they have in common. Okay, so just to remind how this equalizer works. Do you remember the idea behind the equalizer? So what this is saying is a sheaf is a functor, it's a pre-sheaf, such that for all families, the equalizer applies. What is the equalizer requiring f of u to be? You remember? That excellent. So that is true. So that's the fundamental thing, that this and then f of iota and then f of pi sub I has to be equal to iota and f of pi sub j. Do you remember that? But let's unpack that a little bit more. This, you could think of this as the specific, okay, so we've got this map from f of u to f of u sub I. Now, if this is, and I've got some question about how that automatically comes out, but if this is a monomorphism, and for an equalizer, it always is a monomorphism, actually. So maybe that's part of this, that this is monomorphism. F of u is going to be the subset of f of ui's. It's going to be the pairs of the ui's, of the, u1, u2, u3, f of each of them, that are compatible, that give a compatible picture of what's in their intersection. So this is going to be the very specific subpart of these that have matching pants and shirts, in the sense that they both have common picture of what they indicate in this sub area of their intersection. So this is not all possible mappings of, remember, these are like stalks over the UI. If we didn't have to worry about this, we didn't have anything beyond this, this would be all possible assignments from each of the stalks to each of the UIs, right? It'll be like each of the UIs has some stock of possibilities, and the product of these would be all possible combinations of the stocks of possibilities with no consistency checks, no consistency constraints, just all possible combinations. But what this is imposing is consistency constraints. What this is saying is whatever is here for UI, whatever that would depict for the common subset between UI and UJ has to be the same, give the same picture as what UJ posits over that same subset. And so these have to have consistent pictures for what's going over U1 as what's going over U2 with respect to the intersection of U1 and U2. And it has to have common picture of what's going on over 1 and 3 in terms of them agreeing on the behavior over their intersection. And similarly, it has to have in common what's going on between 2 and 3, right? In terms of what they agree is going on at the intersection of U2 and U3. So here, f of u is the subset of this that has a consistent picture for this. That it's the subset that gives a consistent picture for all combinations of I here. Well, for all the use of I's, gives a consistent picture for their intersection with all the use of J's. So Mehdi is absolutely right that the equalizers, you may remember in set, we did this on the board. Do you remember this? So we said, like, if we have x and y and x, and we have two functions, f and g, right? One function f puts maps a to 0, b to 1, c to 0. The other function maps function g maps a to 1, b to 1, c to 0. And we ask for the equalizer. Well, that's the subset of this that are mapped consistently to y. So that's b, because that's mapped to 1 by f and mapped to 1 by g, and c, mapped to 0 by f, 0 by g. It does not include a, because a is mapped differently by f and g, right? So the equalizer gives us the subset of this that is compatible in terms of these maps, that give compatible picture for these maps. And that's what's going on here. This is the subset, the behavior over U as a whole, is the subset of the behavior over each of the UIs considered separately, such that they all agree on their areas of commonality. They all have a common view of what's going on for their intersections. In other words, it's the compatible tuples here. Just like when we had pullbacks, we had compatible tuples of pairs of shirts and pants. Namely, they had to have the same color. Here we have compatible tuples of the f of use of ones. Compatible subset, just those combinations of those that give a consistent picture. Are we good with this idea? So this is like our F, this is like our G. This is the subset of all of these possibilities the subset of all of these possibilities that have a consistent picture of what they map to this, that give the same picture exactly, that map down to this exactly. Okay. Are we good with that idea? Okay. So this is the idea of a sheaf with respect to a Grothendieck topology. And you'll notice that it didn't require any appeal to, a topology in the original sense, this notion, etc. It didn't require, it wasn't set up to specifically reason about continuous deformation or what have you, but it captures these key ideas of topology, and it can represent everything we represented in the original form of the topology. So maybe what I'll do, maybe we'll think about this. So I'm going to ask a question. Suppose we were dealing with a traditional topology where we have coverings like this. So we have sets and we have inclusion, right? Here, that's what we have for our traditional topology for a covering of U. Okay, so what would this look like? Well, the UIs are, say, different regions, right? Like regions like this, say, be different regions. These are different intersections of regions. This is data over those intersections. This is like the behavior over those intersections, the assignment of data for those intersections. This is, again, if just this by itself is all possible mappings of data over these into data over those with no regard for consistency. But the equalizer, this is the subset of those which give a consistent picture of that. So it works with the traditional definition. Let's consider how it would apply here. So if we have those, these are just our inclusion maps, right? Our inclusion maps in our topology, in our covering. UI into U. This is for each of these things here. It consists of the maps into it, which might be also by composition. Well, no, we don't even have to consider composition directly because it's considered in the axiom. Okay, so these would be our inclusion maps. We would have the entire topology for our entire space. We would have X into itself, and so we would have X inside of it. We would have the empty set. And then if UI to U is an inclusion, and we have a family of smaller things that go into UI, then we have inclusions from those smaller things into U, and therefore those inclusions are in our set. And we have these intersections that lie in the common areas for those items. So here, these are monomorphisms. These are monomorphisms. These are monomorphisms. monomorphisms compose. This is a monomorphism. This is a monomorphism, etc. So it works for that case. Now, now let's consider if we have two disjoint ones. Suppose we have disjoint UI and UJ. So they're totally distinct. They're totally separate. So suppose we have here, I'm just going to save this. This is like pulling back over intersections. Okay. Now let's suppose we were to have what would happen if we have this? So sorry, this is going to be our U. This is our U. This is our U. And suppose we were to have the U sub i's be disjoint. Maybe we'll do it this way. Maybe rather than trying to color each separately, I'll just do this. There we go. There we go. So maybe this will be, no, we don't want that. We want it like, oh, okay. U sub 1 and U sub 2. Suppose they were all disjoint. What would happen now with our pullback, with our equalizer? Here's U3 and finally U4. So this would be disjoint regions. So what would this look like? So we have our UIs, we have our U. The UIs cover it, 1, 2, 3, 4. We still have these. We don't have any sub areas. What would these pullbacks be? Here, what would the pullback between U1 and U2 be? Empty. It'll be empty. It'll be empty. That's right. It'll be empty. So it's kind of an uninteresting case here. What would that lead this to be? What would this be? If UI pull back over U of UG, what would this be? This is empty, right? But here, F of turns out F of empty set. Probably I should have explained this first. If we have an empty set, if U is empty set, if U is empty set, there are no sub areas of it. I would have expected one from itself, but there are no sub areas. So this is going to be a point because an empty product is the terminal object. Alternatively, I'm thinking that there may be one from empty set to empty set, in which case this is just empty set itself, but I don't think actually that is the case. I think this is just a single a singleton, which is essentially the terminal object. This is going to be terminal object. So this is going to be a single point, a terminal point, a singleton set. This is going to be a singleton set because a product over an empty set will be a singleton set. And it turns out this f of empty set will be a singleton set as well. And that's going to be basically unconstrained. So this automatically maps that. There's only a unique morphism from a single set to a single set. These two will match each other. This will be the single set subset of that. And so all of these are just points. All of these are just singletons with no particular information content. There's no constraints from the equalizer. There's no constraints at all. If we have disjoint subsets like this will be empty here, the empty set. F of the empty set will actually be a single point, and it'll just be singleton. It's not going to be, there's going to be no behavior over it. The product of those singletons will just be a singleton. This map here will be therefore unconstrained by this. This is a unique map to a singleton. This is a unique map to a singleton. They will match because there's no choice in the matter. They're going to match. This is going to be all products, all possible products. It's kind of like having shirts and pants when there's only one possible color. That's exactly what it is. It's like shirts and pants when there's one color. All shirts and pants match. And therefore, this is all products of possibilities for these because there's no consistency constraint. There's no area of overlap where they have to match. So whatever is possible for U1 can be combined with whatever is possible for U2, can be combined with whatever is possible with U3, whatever is possible for U4. Any combination of those is possible. And so these are just all possible combinations. This is the full set of all of those because this imposes no constraints. This is just a single point that has no, the fact this equals this is given. It's as if these aren't added to this. So this is all given. Yes. 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 Yeah.
Having pullbacks in everybody, but consistency of sections over all problems.
So having pullbacks. So if you're saying if we have a category and we have these objects, these pullbacks between objects give us something analogous to the pullbacks here give us something analogous to talking about the intersections between what's between those areas. And if we consider the behavior over that, that's F of it. That's like the behavior for those common areas. I don't know though if this is addressing your question.
How do you affect,
Yes, in a category.
get the consistency of the, sections for,
No, because you also have to, so having pullbacks lets you express the consistency guarantees. But having those pullbacks, you still need the structure of this equalizer. Because if you didn't have this constraint here, this constraint involving the equalizer, you could have anything going on in U1, U2, U3, U4. There's nothing that from a pre-sheaf. So maybe this is something that will help, Mehdi. Pre-sheaves do not have to honor, like an average pre-sheaf, your typical pre-sheaf is not going to honor pullbacks. So it's not going to map a pullback into a pushout, which is really what a contravariant pre-sheaf you might think it will do. It will not. And so something that's a pullback in the category C does not necessarily turn into a situation where you have matching in terms of the behavior. It matches, Mehdi, when this equalizer applies, but it also matches, Mehdi, when if this functor honors those pullbacks in that category. In other words, honors pushouts in C op. If C has pullbacks, and those are mapped over, so then C op has pushouts, and those are mapped over to pushouts in set, it will honor it as well. What you were saying, Mehdi. That's why we can define sheaves, sort of the high-level definition of sheaves. The two high-level definitions of sheaves are, you can talk about it as a limit-preserving functor. In other words, that this functor honors limits in C, which means it honors pushouts in C op, and it maps those over to pushouts in set. Like that will guarantee it. That will guarantee the picture you're talking about. The other thing that will guarantee it, an alternative high-level definition is you say that if you have this and this equalizer applies for any combination, that will honor, because that forces these UI, without these constraints, you just have all possibilities of what's possible for U1, U2, U3, U4 separately. But with this constraint, it's saying what's going on in U1 and U2 are not independent. What's going on in U1 has to give the same picture for what's going on in the pullback of U1 and U2 as what's going on, the picture of what's going on in U2 gives. In other words, they have to agree on their common sub area, if that's.
But not in each that we have consistency in the pattern.
So,
that is a consistency, but in the basis of it. Is that UI and the hybrid?
So you need F of UI and F of UJ to agree, right? That's what you need. And you can get that with this equalizer by expressing with this equalizer. If what you're dealing with is the subset of these where those agree, the subset of shirts and pants where those agree, you will have that. Alternatively, you could think of it, Meti, as I said, as a limit preserving functor, in which case you're dealing with a push out. Sorry. Yes, a push out situation. Not a pullback situation, a push out situation with respect to this functor. And there, you remember with the idea of a push out, they have to agree on common areas. They're fused around common areas, right? So the picture for the whole is like put together from the picture from the pieces glued together by identifying certain common areas. And you can get it that way. Those are two ways of getting it. This is a way of getting it with Grothendieck topologies, which doesn't require building up a explicit topology which has all unions and all intersections in a traditional sense. I don't know if that's helpful. So maybe what I'll do is talk a little bit about sheaves, and I'm going to stop